Hi, everyone. Welcome to today's demonstration with Andy. And before Andy's lecture, let me do some introduction about Bay Coding Club. Bay Coding Club is a leading K-12 cutting edge of technology and mathematics academy located in Silicon Valley. We bring cutting edge of computer science education to K to 12. And we offer different kinds of computer science like art design, game design, some cutting edge of courses such as Scratch, Roblox, Robotics, Java, Python, USACO, ACSL, a lot of course that you can do some research on our website at baycodingclub.com. And our team, including some of us senior technology and educational experts who worked at like big companies such as Google, Apple, and some of the professors from Stanford and MIT. Of course, we have some of MIT computer science major students as the teacher or your coach. Andy is one of the MIT students who majored in computer science. Yeah, later on, I will do some introduction about him. And this is the roadmap that our Bay Coding Club development we established at 2015. And right now we are at Silicon Valley and we provide all classes online during the pandemic. So I'm Ruby-san. This is about me. Actually, I'm a mom with a 10-year-old daughter, and she also loves computer science, and she attended ACSL last competition, and she went full score in Python, I think last time. And I worked at information technology for over 20 years. And I teach community schools as a computer science basic teacher for Ks. And our Bay Coding Club has very rich of the courses focused in computer science and mathematics. And we have a lot of computer programming courses. Of course, we still have a lot of club, which is very low fees, and you can join like 10 bucks per week, and then you can just meet your peers and do a lot of activities in the club. So just to figure out on our website. And what kind of class we provide? We have group classes, and we have semi-private classes. As you can see, we have a lot of pathways that we set up for Ks. Like if you like game design, we have game design paths. If you like software, and we have a lot of pathways for you. And of course, we have a summer camp right now. Right now, we have the third round of summer camp is about to register. The summer camp for third round of summer camp is started at July 26th. And we have basic of computer science languages, such as game design, Scratch. And we have advanced, we have a medium, we have a specialized of a summer camp for Ks have a special needs to learn, like mathematics, USACO, and auto CAD. We have cybersecurity summer camp. We have Unity 3D game design summer camp too. And if you want to know more information, just call this number or just shoot the email info@baycodingclub.com. I do want to show you a very short advertisement here if you happen to have time to look at it. Can you hear it? Can you hear?
No, we can't hear. You're not sharing your audio.
Well, it's no sound. Can someone hear it?
You can put up the subtitle.
Okay. All right, maybe you cannot hear, but I cannot hear it. it doesn't matter. Okay, go ahead. I don't, yeah, I stop here, and maybe you guys cannot hear what the advertisement. It's just all about our summer camp. If you have any question about summer camp, just let me know after Andy's presentation. Okay, right now, let me introduce Andy. Andy actually is the freshman of MIT in this year, right? And he is the USCO IOI student, and he also have a lot of achievement about mathematics. I'll just give the time and let himself to introduce and to give you the lecture. Hi, Andy, it's your turn.
Okay, can you guys all hear me and see my screen?
Yes.
Great. Okay, so it's so nice to meet you all. So let me just introduce myself first. My name is Andi Qu. I'm from Johannesburg, South Africa, and I will be joining MIT as a freshman starting this fall, and I will be studying computation and cognition. And I like playing the clarinet, video games, building software, and I really like birds. And yeah, so I will be joining Bake Coding Club as a tutor, and I will be teaching a math competition class aimed at kids ages 10+. And yeah, it will be based on the AOPS pre-algebra book. So AOPS stands for Art of Problem Solving. Some of you might know which book I'm talking about, but it doesn't really matter. So yeah, and here's a bit about my math and CS background and this is mostly for the pair. So I've competed in both the International Math and Informatics Olympiad, and I've won bronze medals in both of them. So this is like the level above USACO. Also compete in USACO, so specifically the Platinum division, and I've also set a few problems for it before. And instead of teaching experience, I volunteer as a Math Olympiad coach at a local university. And I'm also a contributor to the USACO Guide, which is a website that basically gives you resources to do well in the USACO. So yeah, now that you know about me, let's see what we'll go through today. So it's numbers. We'll go through what prime numbers are, how we can find them, why we care them, and finally we'll prove that there are infinitely many prime numbers. Okay, also, by the way, any of you have any questions at any time, just feel free to ask me and then I'll answer it. Cool. So first, before we get into prime numbers, I think we need to understand. So basically how divisibility works is, let's say you have 9 candies and you want to distribute them in groups of 3. So if you want to distribute them, and you can do it with no candies left over by just doing that, right? So since you can do this with no candies left over, we say that 9 is divisible by 3. And we can also say that 3 is a divisor of 9. So a way to kind of differentiate between these two is by looking at the suffixes. So divisible, because 9 is able to be divided into groups of 3, right? So yeah.
Or 3 groups.
Now let's say you want to divide it into groups of 4 instead. Sorry, could you repeat that?
Or it's like you can divide it into 3 groups.
Yeah, that also works. That's also, so like 9 is divisible by 3 because there are 3 groups. Cool. So now if you want to divide it into groups out, you can't do that because if you try, you'll always end up with 1 candy left over. So in this case, we say that 9 is not divisible by 4. So now just to check your understanding, here are some practice problems that we can do together. So first, what are the divisors of 12? Can anyone tell me?
1, 1, 2, 3, 4, 6, 12.
Yes. Yes, exactly. So these are the divisors of 12. Is 17 divisible by 1?
Yes.
Yes.
So can you split 17 into groups of 1?
You lag a lot.
Yeah, for me too.
So yes, you can split it in groups of 1, or if you go by the other definition, you can split it into one group. Sorry, my internet must be a bit bad, but is it fine now?
A little bit better.
Let me just try connect to a different Wi-Fi network. Okay, is this better now?
Yes.
Cool. Okay, now, so the next problem is this big complicated number divisible by itself?
Yes.
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 The result
Yes.
is 1.
Yes, exactly. So now is 735 divisible by 4?
No.
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 Yes, exactly.
735 is
yeah,
a odd number, so it's not
Yeah.
divisible by even.
correct. So finally is 1230
Yes,
divisible
they both
by
have a
10.
0 at the
Yes.
end.
Yes.
0.
Yes. Cool. So you guys all understand divisibility. And so you might have noticed two properties. So firstly, every number is divisible by itself. Can anyone explain why?
Because any number multiplied by 1 is just going to be one copy of that number, which is just going to be that number. So multiplication
Exactly.
is basically like just repeated addition, and then division is just repeated
Mhm.
subtraction.
Yeah, exactly. So in the same sense, every number is divisible by 1. So the proof is like the same as Ethan said. So yeah, let's move on. Now we're ready to talk about prime numbers. So prime numbers are basically just numbers that have exactly two divisors, so 1 and itself. You can't split them in any other way. So the first few prime numbers are 2, 3, 5, 7, 11, 13, etc. And so if you kind of just draw out all the prime numbers, you'll see that not many numbers are prime. As you get to the bigger numbers, fewer and fewer of them are actually prime. So yeah, one interesting thing about prime numbers is that 2 is the only even prime number. Can anyone explain why?
Because 2 is only divisible by 1 in itself. I
Yeah.
guess.
Yes.
But all the other
And why is
other number, because 2, like all the other the other number is called composite. Like all the other composite number, 2 is is
Mhm.
1 and itself, and then it's 2 and another number. But 2 will be the same.
So
Yes,
basically,
exactly.
yeah.
That's
Well, I
correct.
have another explanation.
But then it's the same. It's still the same number.
Alright, so basically,
Yeah.
like every even number is divisible by 2, but then 2 is only divisible by itself. So if you do prime factorization, you're going to find that every single even number has at least 1, 2 inside each of them, which we can just what say
yeah.
that
So you
2
can
is the
just divide
only
it into
prime.
groups
Yeah.
of 2. Yeah, exactly. So yeah, and on that note, do any primes end with 0? And if why
No,
or why not?
because then it would be divisible by either 10 or 5
Even.
Yes.
And the number ends with 0
and 2.
even. So even.
Yes. Okay, cool. So yeah, and composite numbers are basically just numbers with more than 2 divisors. So they're just greater than 2 and they're not prime. So most numbers are composite, such as all the even numbers, as you guys pointed out, and all multiples of 10, and so on. So you might be wondering, what about 1? Is 1 prime? Is it composite?
Neither.
It's neither.
Yes, exactly. So 1 only has itself as the divisor, so it's neither prime nor composite. So cool. Now
Is there a
let's move
specific
on
name
to...
for 1?
I mean, they should.
No, not really. It's just 1.
Let's invent a name for 1 and 0.
Yeah.
Yeah, they really should.
Or else it'll be weird.
Do you guys have any ideas for names?
No.
Prime, but it's not prime, and composite, but it's not really composite.
Yeah, just a bit of both, you know.
Comprime.
Quite literally the odd one out, eh? Okay, anyway, yeah, now we can move on to finding prime numbers. So let's check if x is prime. So x is just any random number that we choose, for example, like 131. So the slow way to do this is just check if any number less than x is a divisor of x. So you just count up to 131. Is 2 a divisor of 131? Is 3 a divisor of 131? And so on. So obviously this will take really long, right? Because you have to count all the way up there firstly, and then you have to test all of them. So ideally we'd want a faster way. And luckily there is, because you don't have to check every number. You can just check if any prime number less than x is a divisor of x. Because as Ethan pointed out, you can just use the prime factorization of a number to check for its factors, right? So
Prime
an even
factorization?
faster... Oh, yes, so let me just explain that. So basically, prime factorization is you take a number, let's say x, and then
split it into like the
1 times.
most amount or the most parts possible, and then split those parts one by one.
Yeah, so all of these are prime numbers. Because basically how you can think about this is if you can split something into a bunch of smaller blocks, but well, if you can split them into these blocks, then you can either split each of those blocks into more blocks, or they're prime and you can't split them anymore. So if you just keep subdividing them, you eventually get this thing, which is a product of prime numbers that gives you your original number, right? So then you can just check if any prime number less than x is a divisor of x. And probably the fastest way of checking whether a number is prime or not is only checking up to the square root of x. So do any of you know what the square root is?
Yeah, like the square root is the
Yeah.
A number
what, like a
times,
square root of something multiplied
for
by the
example,
square root of something is just gonna be that
number.
something.
yeah. a
Exactly,
number
yeah.
Square.
Okay, cool. So yeah, let's just check your understanding. Is 113 a prime number? So just for reference, the square root of 113 is less than 11. So basically the prime numbers that we want to test out are 2, 3, 5, 7, and that's it, right? Because we only have to test up to this. So is 2 a divisor of 113? No, it's
No,
not,
it's
because
odd.
113 is odd.
And
Is
3 is
5 a
not.
divisor? Yeah,
No.
3 is also.
Like the 3
5's
and
also
9.
not.
No.
Exactly.
No.
And 7 is also not.
No.
So therefore, since none of these are divisors of 113, we know that it's a prime number. Cool. Are there any questions so far?
Nope.
No.
Awesome. So yeah, now what if we want to find a lot of primes at once? So say we want to find all the prime numbers less than 100. So the slow way to do this is just do our part 1 method on a bunch of numbers. So for example, all of the numbers from 1 to 100, but obviously that's really slow, right? So the fast way to do this is known as the sieve of Eratosthenes. And basically what it is you take a grid or anything with the numbers from 2 up to the number you want to check up to. So in this case, I have 100. And basically what you do is you go row by row and you say, okay, is this a prime number? So since we haven't crossed it out yet, it is a prime number. And if it is a prime number, you just go along and you cross out all of its factors. I mean, not factors, its multiples. So anything that has 2 as a divisor, you just cross out like this, right? And then you go along and the next number is 3. So you say, okay, is 3 a prime number? And it turns out 3 hasn't been crossed out yet. So yes, 3 is a prime number. So then we can basically take 3 and circle it and say it's a prime number, then cross out its multiples, 3, 6, 9, 12, 15, so on. So like this. And then you just keep going. So is 4 a prime number? No, 4 is not a prime number because it's been crossed out. Is 5 a prime number? Yes, 5 is a prime number because it hasn't been crossed out. And you just cross out all the multiples. And then at the end, all the circled numbers are the prime numbers and all the crossed out ones are the composite numbers. So does it make sense why this works? Can you guys explain why it works?
Because like if a number has factors, then it's obviously not prime.
Mm-hmm. And so it will have been crossed out before you get to it.
Wait, so basically we're gonna go to the first row and then we're gonna circle out the ones that are prime one by one and then just remove all of its factors.
Yes.
Okay.
Cool. So yeah, that's how you find prime numbers. And now let's move on to why do we care about prime numbers. So the main reason why we should care about prime numbers is because of the millennium problems. Also just ignore this pop-up, like I did the animations wrong. So yeah, basically the millennium problems are a set of super hard math problems that we have yet to solve. And so these problems are really important. So the Clay Mathematical Institute basically said, okay, if anyone solves one of these problems, we'll give them $1 million for solving
like
it.
For real?
Yes. So the two problems that concern prime numbers are the Riemann hypothesis and the twin prime conjecture. So the Riemann hypothesis is basically saying there's a pattern to the prime numbers, that they're not just randomly distributed, and it gives a formula that lets you calculate it. And the twin prime conjecture says that there are infinitely many prime number pairs that are 2 apart. So like 3 and 5 are twin primes, and like 11 and 13, right? So far only one millennium problem has been solved so far, the Poincaré conjecture. And yeah, it's quite funny because the guy who solved it is a hermit. And basically what happened was he solved it and then he just shut himself in and said, I don't want your money, go away, when they tried to contact him. So yeah.
He was a hermit?
Just the guy who like lives by himself in the woods, basically. He just really liked maths and didn't really care about the money. So
Wait,
yeah.
So who got the money?
The Clay Mathematical Institute just kept it, yeah.
Yeah. What about the other one?
Yeah.
The other ones haven't been solved yet, so maybe you guys could be the ones who solve them eventually.
Like with a very small probability we can.
At least it's non-zero, so
Yeah.
yeah.
Wait, what do you do after you solve it?
You get $1 million, I guess, if
you get $1 million. And also, yeah, it's just really cool if you solve it, because you're like, I solved a problem that no one could solve for hundreds of years.
Then you'd be famous, I guess.
Exactly. Yeah. So another reason why we care about prime numbers is because they keep your computers safe. So it turns out modern computer encryption relies on prime numbers. And specifically, it relies on the fact that really big prime numbers are really hard to find. So you basically take two big prime numbers and you multiply them together, and then that's like an even bigger number. So to factorize that is really hard, and no modern computer can do that yet. So yeah, that's how they keep our computers safe. And there's also quite a lot of money attached to this, because if you find one of those really big prime numbers, you can kind of sell it to cybersecurity people. So I think just a few years ago, someone discovered a huge prime number where, like, if you print all the digits, it's like a 100-page thick book.
Wait, what?
And yeah, that's how crazy it gets. Like, these primes are massive, and that's why our computers are so secure. So yeah, it's like hundreds of thousands of dollars if you find these prime numbers as well. And finally, they're just like kind of interesting to think about. So here's the book that the pop-up was referring to. It's one of my favorite sci-fi books, and I really recommend you guys checking it out if you have the time. So yeah. Now it's finally time to prove that there are infinitely many prime numbers. So first, here's a quote from a Sherlock Holmes book. So basically what this quote is saying is that, like, if you take something and, like, you eliminate the possibility that it's false, then it must be true. So, like, this leads us to a proof method in math called proof by contradiction. So how this works is basically you say, what if the opposite of what we want is true? So this is like, say, what if there are people born in 1865 alive today? Because I want to prove that there's no one born in 1865 alive today. So from this what if, you see, you have to work out what it implies. So basically what that assumption means. And in our case, it means that there are people who are at least 156 years old today. But that's impossible. So our original assumption is also wrong. So
it's just like a guessing game.
Yeah, basically. So you're like, what if? Oh, wait, no, it's wrong. Therefore, it's not this. So therefore, we know that there are people born in 1865. I mean, there are no people born in 1865 that are alive today. So now I'll just take you guys through a basic, well, not that basic, just a proof by contradiction. So I will be proving, I'll be proving that the square root of 2 can't be written as a fraction of whole numbers. So basically, I will be proving that it's irrational for those of you who know about irrational numbers. So basically, we use proof by contradiction by saying, what if the square root of 2 is actually a fraction of whole numbers? So this would mean that we can square both sides and get that 2 is equal to a squared over b squared, where a and b are some numbers that we don't really care about. We just know that they exist. And this means that 2b squared is equal to a squared, right? So since a and b are both whole numbers, you can get the prime factorization of them. And since it's squared, you know that 2 to the power of whatever in its prime factorization must be even. And the same for b. This must be even. But since there's an extra 2, it means that this thing's prime factorization has 2 to the power of something odd. So that means these two things can't be equal, right? Yes?
Will the number be irrational, or will it just be repeating the same number over and over?
I think it'll be irrational, not repeating the same.
Yeah, repeating the same digit over and over can be written as a fraction. So
Yeah, so we'll just get, like, for example, 1.
yeah, so like,
It would be like 1/3 infinite or something like that.
Oh yeah.
yeah. Yeah.
Wait,
So yeah.
I don't really get this.
Okay, so basically, a squared is equal to a times a, right?
Yeah.
So that means if you take the prime factorization of a, so this is 2 to the something, and then you take the prime factorization of this a, that's also 2 to the something, right? So there will be an even number of 2, so 2 times 2 times 2 times something, an even number of times. Does that make sense?
Kind of.
Because it will come in pairs, right?
Yeah.
Okay. Yeah, so since these are different, it means that these can't be equal to each other. So this is a contradiction. And therefore, this thing is wrong. And therefore, the square root of 2 can't equal a fraction a over b. Does this make sense? Okay. Are there any questions?
Wait. That I thought if you were trying to remove the square root sign, you would do square root of 2 times square root of 2.
Yes, but since they're equal, basically, you take a over b times the square root of 2, which equals to a over b times a over b, because these two are equal,
Oh.
right? Anything else?
Wait, is that a 26 to the power of 2?
Oh, no, sorry. So that's meant to be a b.
Okay.
Okay, cool. So you guys all understand. Sorry, yeah? Yeah, that's a 2.
Oh, okay.
So do you guys all understand how proof by contradiction works now?
But why is it 2b? That's probably my last question. Why is it?
Because basically you multiply both sides by b. So basically you bring b here.
Oh.
Cool. So is it all clear now?
Yeah.
Awesome.
Still a
So
bit confusing.
it's fine. You'll get it after next one. So now let's prove that there are infinitely many primes. So our assumption is that like there are only finitely many primes. So what if there are only finitely many primes? So let's say there are n primes, where n is just a random number that's really big, we don't really care about its actual value. So that means we can write out all the numbers, all the prime numbers in an ordered list on like a really long piece of paper. So we can number them P1, P2, P3, and so on, where Pn is the largest prime number. So now consider this number, which is basically just the product of all of the prime numbers, and then plus 1. So if you try to determine if this is a prime number by using our part 1 method, which is just testing whether each prime number is the divisor of this, you'll find that you can't split it evenly into prime groups, right? Because if you try to split it into prime groups, you'll always have exactly 1 left over. So that means that this number is also prime. Okay, but this number is bigger than the largest prime that we have, which is impossible because we assume that it is the biggest prime. And so this is a contradiction, which means that there are infinitely many prime numbers. Does this make more sense?
Yeah, I do.
I
If you-
guess.
The only reason that I kind of got confused is because I forgot remember you said the slow way and the fast way. I forgot the fast way to find it.
Yeah,
But if
sorry.
you remember the fast way, then this makes sense.
Sorry, could you repeat that?
I think the reason that you can't split it evenly into prime groups is like the fast way of doing the fast way method you said was like
Yes.
it was like you do like prime numbers and find their divisors or something.
Yeah, so the first way is basically check if you can split the number into prime groups, right? So like if you want to check if 9 is a prime number, you check if you can split it into 3 groups because 3 is a prime number and you can. So therefore it's not a prime number. Does that make sense? Are there any other questions?
No.
Okay, cool. So yeah, that's pretty much it for this lecture. Here's just a summary of what we went through today. So firstly, if you can split A into groups of B, then A is divisible by B, and B is a divisor of A. That's the definition of divisibility. Prime numbers are numbers with exactly 2 divisors, and you can use prime numbers to check whether other numbers are primes. You can use the server of Eratosthenes to find many primes quickly, and we care about prime numbers because of a number of reasons. And finally, we proved that there are infinitely many prime numbers. So here's just some homework for you to do. There are also 2 bonus questions. So yeah, we proved this example thing just now. So another nice problem that you can prove is prove you can't draw a regular hexagon in a square grid. So by square grid, I mean like one of these grids where each vertex must be on here. So yeah, that's another cool problem. And while you guys just jot down these problems, I'll let you guys have I'll answer any questions that you guys or the parents may have. So are there any questions?
Yeah, sure. Andy, thank you so much for the presentation. And we do get some of questions along with the registration. Are you ready for answer them first and then the question
Okay.
from is right now? Yeah, one of the parents asked which grade is suitable for your class?
So this class is targeted for kids ages 10 plus, so it teaches pre-algebra. So I'd say probably grades 4 to 6.
Okay.
Yeah.
Yeah, thank you. Some of parents are very curious about your application of MIT. So they come along with the question is, do you think your mathematic competition is helpful for your apply for MIT?
Yes, I do think it's very helpful because firstly, it lets you get better test scores. So for instance, because I did a lot of competition math, I found the SAT quite easy. And secondly, MIT just really likes math competitions. So if they see that you did some, then they'll be like, ah, this kid's smart. And they'll like think of you highly. So yeah.
Okay. The third question here is, the parents notice that your USCO IOI, which is very few people can get that level. So they ask, do you think the mathematics is correlate with the computer science? What do you think about math and computer science?
I think they go hand in hand. So a lot of the USACO people I know also do USAMO because it's just all about problem solving, right? So if you can do problems in math, and you can also program, then you'll also be really good at USACO.
Okay, yeah, cool. So there's one parent ask about the USACO. So they notice that you're the USACO IOI, which is very high level, but they ask which grade you think can attend USACO bronze?
I think USACO bronze should be 8th grade and up, but I think also 6th and 7th grade can do it. Like a lot of people do 6th and 7th grade USACO because it's always helpful to start early. So yeah, as long as they know how to program, it's fine.
Yeah, thank you. This is I selected 4 of the questions from the registration form. So right now we open the chances for the parents here. Everyone, we appreciate Andy's lecture. If you have questions, you can open your mic and ask. Or you can raise up your hand here. Do you have any questions about today's mathematics presentation? Whatever about Andy's math competition before? So how many of you wants to attend the math competition? Oh, how many of you are on the way with the math competition right now? I believe all of you are like mathematics, because here we teach math as an art, so we teach the art of problem solving, right? Okay. Anyone has any questions here? I know some of the kids are Andy students. It's gonna be new class, set it up. Okay, all right. I believe we answered most of the questions from the registration, and if they still have questions, I believe they can call us, whatever. Add contact with us. Let me show you again. This the confirmation contact more information with us here. And you can shoot us email at info@Coding Club or call us at 650-254-6886. Okay. You guys ask at the last minute. You guys have no questions? You can open your mic. Okay. It seems like they don't have any questions here. It doesn't. It's cool. Okay. All right. So I think pretty much all for today's presentation and for Andy's class. And also Andy, maybe, yeah, in the future, he is gonna tutoring the musical or you're interested in mathematics, pre-algebra. So contact with us that this email and log on our website and call us. Okay. I think pretty much all for today. Andy, do you have any summarize for today?
No, that's all for today. So yeah.
Okay, thank you. Then we can stop here. I do see a chat, maybe a question come along with. Sorry, I didn't see the chat. Well, okay, all right. Yeah. Andy, do you guys have any question about the chat? Repeat the same number? No, no. Okay, that's good. Okay, that's stop here and welcome to join our club. We have Python club, game design club, Minecraft club, even Roblox club. If you guys want to join our club and have a fun with your peers, just join our club on our website. Okay, we finish all today's mathematics presentation and hope to meet you again. Thank you so much for show up here. Bye. Bye.
Bye.
Bye.